Okay, we are going to look at calculating the line currents of an unbalanced delta resistive load. So here's an example of an unbalanced delta resistive load. So we've got three resistors connected up in delta. RA to B is 10 ohms, RB to C is 20, RC to A is 30. So what I've also done here is constructed a phasor diagram, and I put our line voltages or phase voltages in delta V lines the same as V phase. Already plotted on there. So we got our VAB, VBC, and VC to A. Okay, so one of the ways I like to set this up and keep it nice and organized is going to start calculating currents, and as I go through, I'm going to keep it nice and organized, and I'm going to do the opposite vector immediately. So let me just show you what I mean. So I'm going to go ahead and I'm going to calculate phase current A to B. So I A to B is equal to the voltage A to B divided by the resistance A to B. So 240 over 10 ohms is equal to 24 amps. And because it's a resistor, current, this phase current, stays right in phase with the phase voltage A to B. So it's at 0 degrees. So if I plot that on the phasor diagram, I will put IA to B right at 0 degrees in phase with voltage VAB. Now while I'm here, I know I'm going to need the opposite vector of IA to B for another calculation. So while I'm thinking about this, I'm going to go ahead and figure it out. So IB to A, which is the opposite of A to B. It is still the same magnitude, 24 amps, but now it's 180 degrees from IAB. So I can go ahead and plot that out. IBA is 24 amps at 180. IB to A. Next vector I can calculate is I can calculate current from B to C, so phase current BC. So I'm going to take 240 volts and divide it by the resistance BC of 20 ohms. That comes to 12 amps. Now because it's a resistor, that 12 amps of current is going to be right in phase with the volt drop BC. So I plot it right at 240 degrees. And there it is right there. IBC is 12 amps. All right. So while I'm thinking about that vector, I can also figure out the opposite vector for it. The opposite vector would be IC to B. So that would be the same magnitude, 12 amps, but it's at 180 degrees from IBC. So 240 subtract 180 is at 60 degrees. So I can plot that out. IC to B, 12 amps at 60 degrees. The next vector is IC to A. IC to A is equal to voltage C to A, which is 240 volts, divided by the resistance in C to A, which is 30 ohms. That comes to 8 amps. Because it's a resistor, the phase current in C to A stays right in phase with phase voltage C to A. So I have to plot that right at 120 degrees. IC to A. Now, while I'm working on IC to A, I know I'm going to need the opposite vector, IA to C. IA to C is going to be equal to the same magnitude, 8 amps, but now we're 180 degrees or opposite direction to voltage C to A. So 120 plus 180 comes to 300 degrees. So I'll have to plot 8 amps at 300 degrees. Okay, so I have got all of my phases up here. And if we recall, for unbalanced circuits, we have to add up each phase individually. So if I got current coming up, and I want to figure out what line current IA is right here, I know it's going to be phase current IA to B plus IA to C. So that's these two, top and bottom, A to B plus A to C. If I want to calculate IB, current comes into here and it splits, and I have to get current B to A plus B to C. If I want to calculate line current C, current comes in here, splits, goes from IC to B and IC to A. So you see these two form, when we add those together, IB. These two are IC. And the top and bottom, they are IA when we add them. So let's go ahead and add them. Our formula for unbalanced, well, works for both balanced and unbalanced, but we have to use it in unbalanced circuits, is IA is equal to phase current IAB plus phase current IAC. So IAB is 24 amps at 0 degrees plus IA to C, 8 amps at 300 degrees. It comes to 28.8 amps at 346.1 degrees. And if I plot that out, ends up right there. There's my line current. If you're using your calculator to determine this, it will give you a negative angle of 13.9. So we have to take 360 and subtract that 13.9 degrees to express it as a positive angle, 346.1. For calculating IB, I take my IB to A, 24 amps at 180 degrees, and I add it IBC, 12 amps at 240 degrees. It comes to 31.7 amps at 199.1. Once again, our calculator gives us a negative angle, so we have to take 360 degrees and subtract 160.9 degrees to give us 199.1. If I plot that out, it's going to end up in between the two vectors we just added and closer to the larger vector. Last line current, IC. IC, we add IC to B plus IC to A. So that's these two. 12 amp, IC to B, 12 amp at 60 degrees plus IC to A, 8 amps at 120 degrees. It comes to 17.4 amps at 83.4 degrees. I'll plot that out. Once again, it ends up in between the two vectors and closer to the larger one. Hopefully that helps you. I find this method really keeps it nice and organized on what two vectors to add.